It's great to be here. Thank you for having me. So my name's Naomi. I'm in the final year of the Quantum Engineering CDT at the University of Bristol. This is joint work with Ollie Thomas, who's here, and Dara McCutcheon, who both work for Duality Quantum Photonics. So we're a startup in Bristol working on integrated quantum photonics. If you want to know more about what we do, feel free to come chat to us. So I'm going to be talking about Gaussian boson sampling. I'm going to assume people aren't that familiar with it, so apologies if some of the background is boring to you if you know about it already. I'm going to talk about a particular application of Gaussian boson sampling called dense subgraph finding, and we're going to be looking at how effective it is when you apply different sources of error to GBS, and talk about the effectiveness of GBS for this problem based on that. So Gaussian boson sampling is a framework for photonic quantum computing that's experimentally simpler to implement, but it's non-universal, and because of that, we have a more restricted space of applications. One of these potential applications is called dense subgraph finding, which is a graph theory problem with implications in lots of different fields. What we found, so the main outcome of this work is that quantum-enhanced, so GBS-enhanced dense subgraph finding algorithms seem to be very robust to different sources of error. This is interesting partly because we know that experiments, when GBS has a high level of error, it actually becomes efficient to classically simulate. So this would suggest that even though it's effective for this problem, there could be classical solutions instead, and I'll talk a bit more about what that means. Yeah, that's the whole thing. These are the references. So number one is our paper. Number two is your GBS paper if you're not already familiar with it. Number three is a reference that I'm going to be talking about a lot throughout this work. So this was the initial connection between GBS and dense subgraph finding. So we use the same techniques that they do in this paper. Our work is based off their algorithms. Really, the real meat of this study is their emulator, now maintained by Duality Quantum Photonics. So that's Quantum Gaussian Optics Toolkit, which is online, and it's based on this framework, which is what we use to model different sources of error. If you're interested in using that, there's one in C++ and one in NIM. Again, feel free to chat to us or email us. If you want to know more about simulating GBS, I think the documentation from the Walrus, which is maintained by Xanadu, is really helpful. If you want to know more about dense subgraph finding, there are some good slides from Moses Charaka, which I recommend. And finally, I'm going to be referencing this paper a lot, which is talking about the different noise thresholds that GBS has to pass before it's classically simulable. So photonic quantum computing is hard for a number of reasons. One of the big roadblocks that we have to overcome is measurement and feed-forward. So that's the process where, later parts of your calculation are going to depend on measurement results from earlier parts of your computation. So this is difficult, and basically the idea behind boson sampling is what can we do without this? So instead, we have a passive linear interferometer, and that means there's no measurement and feed-forward, there's no active elements. We start with individual photons, we fire them into our linear interferometer, which applies some unitary, and then we make photon number resolving measurements at the end, and we come out with a click pattern, some measurement pattern that tells us where our photons ended up. It's worth saying from this point forwards, instead of talking about qubits, I'm going to be talking about photons in modes. So I'm going to have a number n spatial modes, and I'm going to be talking about where our photons start and end. I'm also going to be talking about the collision-free subspace, which means I'm going to assume that our final measurement pattern is just a series of ones and zeros. So the work by Aronson and Arkhipov shows that this is a basis for quantum advantage because it's inefficient to classically simulate. That is, it's inefficient for a classical computer to keep track of this quantum state. Although, of course, if you know your quantum state, you can use the Born rule to work out the measurement probabilities at the end. So what we're really interested in are the probabilities of different outcome patterns, different click patterns that tell us where our photons end up. So in order to calculate these, we're going to start with a matrix describing our interferometer, which is how our state evolves. Then we're going to take a submatrix of that unitary according to where our photons started and ended. So we're going to select columns according to what modes they were input. So for example, here we input photons in modes 1 and 2. So that means we're going to select columns 1 and 2. And then we're going to select rows according to where our photons are output. So in this case, we measured photons in modes 2 and 4. So that means we're going to select rows 2 and 4, and this is going to give us some submatrix. Then we take the permanent of that submatrix, which is a function like the determinant, but without the plus and minus signs. And this is going to tell us our probabilities of our different output patterns. So this permanent is the bit that's difficult for a classical computer to calculate. Gaussian boson sampling is a similar setup, but instead we're inputting a Gaussian state, which is a continuous variable state. Unlike with traditional boson sampling, we don't have a fixed photon number, we have a superposition over different photon numbers. I'm going to assume that our photons are all produced by squeezing and not displacement. Essentially what that means is that our state over n modes can be described by a covariance matrix, sigma, which is size 2n by 2n. Importantly, as long as you're applying these passive optical transformations, you're still in the Gaussian formalism. So that means that you can follow the whole evolution of your quantum state through matrix multiplication on this 2n by 2n covariance matrix. And that means that actually up until the measurement stage, this is efficient for a classical computer to do. It's just measuring when that's a non-Gaussian operation, and that's the bit that's difficult to calculate. So you can kind of think about this in a slightly different way where, say, we're creating this arbitrary continuous variable quantum state, and then we're doing the difficult bit, which is making photon number resolving measurements on it. So once again, we're interested in the probabilities of different outcome click patterns. So these outcome probabilities are given by the hafnian. Once again, we're going to describe our interferometer by some matrix. This is going to be our matrix A, which is related to the covariance matrix. It's not that important to worry about how they're related. We end up with some matrix. And once again, each of our click patterns, our different click patterns, is going to be related to a different submatrix. Previously, our submatrix was chosen according to where we input photons and where we measured them. This time, our submatrix is just going to be selected according to where we measure them. So here, we measured photons in modes 2 and 4. That means we're going to select columns 2 and 4 and rows 2 and 4. And that's going to give us our submatrix. We take the hafnian of the submatrix, which is a matrix function that's difficult for a classical computer to calculate, and that's going to tell us our probabilities of those different click patterns. So the hafnian, this is what it looks like on a matrix, but if you imagine your matrix is representing a graph, which I'll talk a bit more about later on, then what our hafnian does is it pairs together vertices. So what it does is it counts all of the different ways that you can pair vertices that are connected by an edge, so that each vertex is part of one pair. Another way of thinking about this is how many different subsets of your edges are there, so that each edge is connected to exactly one vertex. Each vertex is connected to exactly one edge. So Gaussian boson sampling is the framework that a lot of recent quantum advantage claims have come from. So for example, from USTC and Xanadu. Gaussian boson samplers don't just tell you hafnians of matrices. What they do is they spit out samples. So they give you a series of click patterns according to some underlying distribution. And that distribution is found by calculating hafnians. So importantly, it's not just difficult to calculate those individual probabilities, but it's also difficult for a classical computer to spit out click patterns according to the underlying distribution, or indeed a similar distribution. So that's what you would be doing if you were simulating your Gaussian boson sampler. You'd be looking for a classical computer that just gives you these click patterns, these lists of ones and zeros, and that's something that's also difficult to do. So that's Gaussian boson sampling. Next, I'm going to talk about the problem that we're trying to solve. So that's dense subgraph finding. We start with some input graph, by which I mean a set of vertices connected by edges, and that's going to have some density. The definition of density that I'm using is normalized, so between 0 and 1. So that is a graph with no edges in it would have density 0, and a fully connected graph would have density 1. So the problem that I'm trying to solve is I'm going to give you some graph, and I'm going to give you some number k, and I'm going to say what subgraph, so what subset of vertices of size k is the most dense, so has the most edges in it. This is an NP-hard problem to solve, so therefore we don't expect a Gaussian boson sampler to be able to solve it with 100% accuracy in polynomial time. It's a generalization of an NP complete problem, which is clique finding, so saying, is there a fully connected subgraph of size k? This is relevant to many different fields. I think most interestingly in molecular docking, which is a component of drug design. If you're interested in that, I have some backup slides on it, which I can go to. So then classical algorithms to solve this problem, they can be deterministic, so they can give you a particular output, or they can be stochastic, so that means there's an element of randomness in it. What we're looking to do is enhance these stochastic algorithms using the statistics from Gaussian boson sampler. Like I said, for complexity reasons, we're not expecting to be able to solve this problem perfectly, but hopefully we can improve these stochastic algorithms. So I'm going to be focusing on unweighted, undirected graphs, which means our edges don't have a weight or a direction. And these are represented by an adjacency matrix A. What that means is that this is a symmetric matrix where the element ij is a 1 if vertices I and j are connected by an edge, and it's a 0 if they're not connected. And what we're going to do is we're going to encode this in our covariance matrix that our Gaussian boson sampler produces so that our output clique probabilities are proportional to submatrices of this covariance, submatrices of this adjacency matrix. And our outcome probabilities are going to be proportional to the hafnian squared of those submatrices. So this is how we find our covariance matrix. And there's also this extra degree of freedom C, which is essentially going to tell us how bright our squeezes are, how bright our sources are. So this is going to tell us basically what submatrices have the highest hafnians, because those are going to be the most likely outcomes. We know that the hafnian counts the number of perfect matchings in a graph, and previous work tells us that the number of perfect matchings in a graph is lower bounded by the number of edges. This reference that I mentioned before confirms that there's a correlation between density and the size of the hafnian, the number of perfect matchings. Basically, what this tells us is that if we are given subgraphs of higher hafnians, then they're likely to be the ones that are most dense. So they're going to be useful outputs for us. So this is how we're using Gaussian boson sampling to answer the problem. We start with some graph, and we describe this by an adjacency matrix. Then we choose an appropriate covariance matrix, which is how we encode our Gaussian boson sampler. Then the most likely outcomes of our Gaussian boson sampler are going to correspond to subgraphs that have the highest hafnian and therefore also have the highest density. So once we've programmed our Gaussian boson sampler, it's basically going to be spitting out better answers to this problem. So hopefully we can use this to enhance our stochastic algorithms. So previous work looks at how well these quantum-enhanced dense subgraph finding algorithms work. So on the right-hand side, we have a stochastic algorithm called simulated annealing, which I'm not really going to go into detail about today, but I do have backup slides on it. Again, if you're interested in it, it is covered in our work. On the left-hand side, we're going to look at a slightly simpler algorithm, which is just random sampling. So what I mean by that is our grey line, that's going to be our classical algorithm. So if we're trying to solve this problem classically, we're going to start with some input graph that has size 30, and they're going to say, I want to find the densest subgraph that has size 10. What you're going to do is you're going to take, for example, 400 samples. So you're going to take 400 randomly chosen subgraphs of size 10. You're going to compare them all, and you're going to keep the one that has the highest density, and that's what we're putting on our y-axis, the one with the most edges. Then for our quantum-enhanced case, instead of randomly choosing those subgraphs, we're going to take them according to Gaussian boson sampling. So we're going to run our GBS experiment. It's going to give us a certain number of samples, and we're only going to keep the samples that have the right number of clicks. So remember that our outcomes don't have a fixed number of photons. So because we're looking for subgraphs of a fixed size, we can only keep certain outcomes, and those are the ones with a fixed photon number. So here we're only going to keep outcomes that have 10 clicks, and those are going to correspond to subgraphs. We're going to compare them, we're going to compare the density, and we're going to keep the ones with the highest density, and that's what we're plotting on the y-axis. This dotted line is a comparison with a deterministic classical algorithm, just for a benchmark. And you can see they're actually struggling to find the densest subgraph. So as a first step, we just wanted to see that we could get similar results. So our input graph was size 24. Our output graph, so we were looking for the densest subgraph of size 8. Here, number of steps, again, that means that we've just kept the click patterns of 8 clicks. We find all of these associated subgraphs, and we keep the one with the highest density, which I plotted on the y-axis. And you can see, again, quantum is outperforming classical, particularly when we're only taking very small steps. So it means it's giving us a good speed up to this algorithm. What we want to do now is we want to input different sources of error and see how well it performs. So first of all, we're going to use impure sources, so spectrally impure sources. More information on what that means is described in the appendix, but essentially it's degrading the quality of our classical interference. And you can see that even with very low purity sources, our experiment is still performing really well. It's still really robust to error. Yeah, I think that's pretty clear from the graph. It's very close to the no error line. It's easily outperforming the classical case. It's also worth mentioning that our best subgraph was density about 0.69, so it's actually finding it. With loss, again, so this is 60% end-to-end loss, so if you put in a photon at the beginning, there's a 60% chance that you're not going to measure it at the end. It's a very high amount of loss, and it's still performing really well. Great. That was just looking at one particular input graph. Here we're going to scale it up a little bit and see how well it performs. So here, for each graph size, we chose a random input graph, and then we looked for subgraphs of size root n for input graph size n. What we did is we just took 1,000 samples and then averaged over the density of all of those samples. So again, classically, we just chose them randomly, and then quantumly, we chose them according to GBS. Again, with high levels of error, it's still doing really well. It's still producing very high density samples. Finally, this graph is showing something that I think maybe I swept under the rug a bit earlier, which is we don't always output the correct size sample. So if our input graph is size 24 and we're looking for a subgraph of size 8, that means we only want to keep click patterns that have 8 photons in them. So in this case, we run it as before, but we say we're actually going to keep all the samples that have the wrong size, and we're just going to say those have density 0. So this is basically telling us a more realistic picture of how many samples we're actually going to have to draw to get useful answers. You can see that it takes a little while for quantum to catch up in this case, because a lot of the time it's going to be spitting out answers that aren't particularly useful to us, but eventually it does outperform classical. I also want to point out, so if you have large amounts of loss, you're more likely to get click patterns that don't have many photons in them, because you're losing your photons as you go through. So actually, we adjusted the brightness. We adjusted this parameter C for each loss case so that we were optimizing for the right number of clicks. So we were outputting slightly different quantum states with each of our loss values. We're assuming that if you're running the experiment, you know basically what your loss is going to be. So let's talk about what these mean. As I mentioned before, if you have different sources of error in a Gaussian boson sampling experiment, this makes it easier to classically simulate. So if you're trying to run a quantum advantage experiment, you need to show you're above certain, I guess below certain error thresholds to actually claim quantum advantage. This is very well understood for loss in distinguishability, less so for spectral error, but it's still suggested. So in particular, if we're looking at loss, the amount of loss that we can tolerate and still have a Gaussian boson sampling experiment that's inefficient to classically simulate depends on how bright our sources are. It depends on what our state is. So remember, for each of our loss lines, we're looking at a slightly different quantum state. So that quantum state that we used when we had 0 loss, if we'd have had 43.7% loss, we would have been producing something that's classically simulable. On the other hand, the quantum state that we produced for our 60% loss graph, this has a slightly different threshold because it has a slightly different brightness. So if that suffered over 47.3% loss, which we're assuming it did do, then that becomes classically simulable. I think maybe this slide is a little bit convoluted. So the main takeaway that you need to get from this is that once we've gone over the 60% loss line, which is what we were simulating, that's crossed the threshold into being efficiently classically simulable. However, I want to be clear, this isn't the method that we use to simulate it. We use the emulator and we use the same method for all of those lines. So we didn't actually use the method that was described in reference 8, which is the efficient method to simulate it. And it's also worth saying this is maybe not even the optimal way of approaching it, which I'll come back to in a minute. So if you have a Gaussian boson sampler and you want to solve the dense subgraph finding problem, it is going to be resilient to error. So there's lots of reasons why you might have a Gaussian boson sampler in your basement, like you're trying to produce GKP states or something like that. And in that case, it is going to be useful for dense subgraph finding. However, there is a suggestion that because these classically simulable states still give you very good solutions, if you're wanting to solve the dense subgraph finding problem, there you may not even need to build your Gaussian boson sampler because you can bypass that hardware stage and just simulate it instead with a very high amount of loss, and that could give you a useful solution, potentially. There are some problems with that in that the methods that we use to simulate high loss states have their own issues in terms of they'll have some error, and we need to look further as to how that error is budgeted to see if it's still a good solution. But this is a potential implication of the work. Again, is this a fair comparison of the classical case? What we were really interested in here is comparing quantum and quantum, so no error quantum and high error quantum, rather comparing quantum and what they would actually do in a classical case. So it may not necessarily be that we phone up the classical algorithms people and we say, why don't you just try simulating high loss Gaussian boson sampling? So this is kind of the next steps for the work. First of all, we could look at, we were suggesting to look at quantum-inspired classical algorithms for dense subgraph finding, and then actually this paper came out recently which does exactly that. It kind of goes through a slightly different route, and actually it shows that it is possible to simulate hafnians of matrices of all positive elements within a reasonable error budget to solve this problem, which is quite exciting. It could be, it's worth asking whether this applies to other uses of Gaussian boson sampling or not. It could be that this is just because of particular artifacts about quantum states that are based around graphs, in particular that you're taking hafnians of all positive valued matrices, which is suggested to be classically easy. So that's an area of future work. Finally, it might be interesting to look at different input states, in particular classical input states, because it could be that this isn't necessarily a quantum interference effect, and that's why it's so robust. So maybe this is something that we could be doing with classical optics instead. In a slightly different vein, there's been some work on Quandela where they looked at answering this problem with traditional boson sampling instead of Gaussian boson sampling, which I think is also another interesting route to look at. So to summarize, Gaussian boson sampling has applications in dense subgraph finding, and that's still true, and it is still useful in this case. We simulated GBS with different sources of error, and we found it was very robust, which suggests that you could bypass building the hardware if you're doing it just for the sake of solving these graph problems. But more work is needed to verify that. Thank you.
Thank you very much. We have time for questions.
Yes, thank you for the talk. So just to make sure I understood, you're running simulated annealing with like a random input state, and then to compare to simulated annealing with an input state coming from Gaussian boson sampling. Is that right?
Yeah, so the simulated annealing case is a little bit different because you have, so simulated annealing, you start with a random subgraph and then you kind of have this search phase. So we actually use GBS both in seeding, where you start, and also in your search phase. So it takes a few more samples. I can give you the results for that. They look pretty similar.
I was just wondering, do you know how it compares to like simulated quantum annealing?
I think like they're quite separate.
Okay.
yeah, like simulated annealing. Annealing is this idea that you start with you kind of like how you search the space. But I don't necessarily think that quantum annealers would give you. They potentially could. I'm not an expert on quantum annealers.
Well, it's just because simulated annealing is normally the benchmark for quantum annealers.
Okay.
So I'm just curious how these three different things would play off each other.
Yeah, I don't really know enough about quantum annealers to answer that. Sorry.
And then brief curiosity question. You said you're using squeeze states rather than displaced states. Displaced states are also Gaussian. Is it easier to work with squeeze?
Yeah, so they're also Gaussian, but they're essentially classical states. So I won't go all the way back through this actually, but when we're looking at how to represent our Gaussian state, we'd have our covariance matrix and we have our displacement vector. And then when we're representing that as a graph that we take our hafnians of, our covariance matrix is telling us where our edges are, and then our displacement vector is giving us loops on those edges. So instead of taking the hafnian, we take something slightly different, which is the loop hafnian, that I actually don't think gives us quite as useful outcomes in this problem. And it's also adding in displacement doesn't make it harder to simulate or more complex to simulate, so it's not giving you any extra quantum advantage.
Thanks.
Hi. We've been trying to keep up with the visual puns going on in your slides. We have a question about the image in the Huff slide. Is this a village in Germany?
Oh, sorry. Hafnian comes from hafnium, which is the Latin word for Copenhagen. So that's a picture of Nyhavn in Copenhagen.
Thank you.
Thanks very much. I'm just wondering if there's time, can you say a little bit more about your work on the application to molecular docking, please?
Yeah, this isn't actually my work, I should be clear. This is other people's work, but it is interesting. So molecular docking is where you have two molecules and you want to know how they fit together. So you have a drug and a protein. So this can be represented by a graph. So let's say there's like 5 active sites on your ligand and 5 active sites on your receptor. Each of those possible combinations of like A1, A2, A3 are going to be represented by a different point. And then those points are going to be connected if it's mutually compatible. So if you can have, your thumb and your first finger together at the same time, there'll be an edge between those connections. But having your first finger and your first finger and your first finger and your middle finger connected simultaneously is not allowed, so there'll be no edge there. So what you're looking for is a clique. You're looking for a set of combinations that's all mutually compatible, and that's going to be based on things like energy levels and distances in your molecule. So essentially you input, this is also going to be weighted, which actually isn't too difficult to do. It just complicates the matter slightly. So you input your weighted graph into your covariance matrix, and then you're looking specifically for cliques of a certain size.
And depending on the application, was there any comparison to classical work in that area, or perhaps the problem?
If a lot of docking simulation software is using these graph search problems. So a speed up in that case would be really useful. But they also have the issue that you need a very high throughput of data. It's not necessarily always the case that you have one big problem that's really hard to solve, but actually you're looking for a significant speed up so you can solve the problem lots of times. So it would depend on really hardware constraints. So actually, in the case of molecular docking, the size of the problem fits really nicely into like quantum advantage, because actually you're going to be looking at graphs of size, say 100, with subgraphs of about 10 or so, which is going to be the size of the hardware that we're interested in, but we're also going to need a high level of programmability for that.
Thanks very much.
Thanks very much for the talk. I just wanted to, just so I make sure I understand, the last advantage graph you showed for the lossy case,
Yeah.
where so initially in the first graphs where there's quite a big quantum advantage, you're post-selecting on getting the right number of clicks.
Yeah.
So here you're kind of keeping everything, and then just if there's the wrong number of clicks, you set its density to 0.
Yeah.
Okay, but this is, as it were, deterministic though now. Okay. Right.
So yeah, that's true. It's also worth saying, I didn't really have time to go into this, but you wouldn't necessarily just throw those away. It's not too hard to, if you're looking for a subgraph of size 8 and you find one with high density that's size 6 or 10, it has to have an even number of vertices, I should say, then it's not too difficult to search the space based on that and just add a couple of vertices in. So the fact that we're just throwing them away and we're still beating the classical case, actually quantum would probably do even a little bit better than that.
Okay, cool. Thank you.
All right. I think let's go ahead and thank the speaker again.